Welcome back, friends. In today's class, I'll be talking about the mechanical energy in an isolated system. That's what I'll talk about. So let's take a system. Let's say this is a system and this is separated with the boundary. This is a boundary. Outer edge of the system is a boundary. And this is surroundings. Now, isolated system means no energy is being given to the system, no energy is being taken out of the system. That system is called an isolated system. On top of that, there is no mass transfer also, so neither the mass nor the energy is being transferred from the system. So I'm going to take an example for the projectile motion, how we can apply this isolated system, mechanical energy of an isolated system to a projectile motion. Let's say you're throwing a projectile from here at an angle of 30 degrees, and this projectile follows this trajectory and lands on the ground at this point. So when you launched this projectile from this point, initially it was traveling with the velocity of 20 meters per second, let's say at location 1, when you shot it, and there was some potential height because you've thrown it from the cliff, so the height is h. Or I'm going to give it as 10 meters also. So what will be the potential energy? Potential energy value will be equal to mgh, and the kinetic energy in the projectile will be half mv square. So mechanical energy in the system will be equal to potential energy plus kinetic energy. So potential energy is mgh plus half mv square. Let's say this projectile is a ball, and the mass of that ball is, I'm gonna assume 1 kg, just to make my calculations a little easier. So 1 times I'm gonna assume g value as 910 rather than taking as 9.81. I'm just assuming it as 10. Just again, the idea is to make the calculation a little easier. So this times 10 plus half times 1 times this is 20 square. 20 square is 400. 400 divided by 2 is 200. This is 10 times 10 is 100. So the mechanical energy in the system comes out to be 300. So this is the mechanical energy at location 1. At location 1, the mechanical energy is 300 joules. So if when you're gonna throw, if it is an isolated system, when you shot this projectile, the total mechanical energy, even at location 2, mechanical energy, and this is the location 2, will also be 300 joules. And if this is the location 3, the mechanical energy will also at location 3 will be 300 joules. In fact, the mechanical energy throughout will remain 300 joules. At this place it will remain 300, at this place, everywhere it will remain as 300 joules. But what's gonna change? The thing which is gonna change is the potential energy and the kinetic energy. So if the projectile, when the projectile was somewhere here at the initial location, I'm gonna change the color. So this is the initial. So at here the potential energy was 100 joules. Here the potential energy was 100 joules, and the kinetic energy was equal to 200 joules. Now when it reaches on top here, so I can say that the mechanical energy at this location will increase, because the potential energy, the potential energy will be because of this height, because the height has changed, and there will be a reduction in the kinetic energy, because the vertical component of the velocity keeps on reducing with the period of time. But again, when we talked about projectile motion, remember we said that the horizontal component does not change, because we consider the air friction as the negligible. So in short, I can say that the kinetic energy will reduce and the potential energy will increase, but the total mechanical energy will remain the constant throughout every point of this trajectory. So this is the concept we're gonna follow. Let's look into an example based on this concept. So a frictionless roller coaster car has a mass of 8 times 10 raised to the power 2 kgs at first point of its journey, the car has a speed of 4 meters per second and is 35 meters above the ground. So this is at a height of 35 meters above the ground. So this is from the ground. This is equal to 35 meters. And now if it is at a height of 35 meters and has a speed of 4 meters per second, at this location, another thing which is given to me, that the speed is equal to 4 meters per second, and what is later its speed is measured to be 20 meters per second. Somewhere down its speed is increasing, so it means some of the potential energy is getting converted into the kinetic energy. Calculate its initial mechanical energy relative to the ground. So at location 1 I wanted to find the mechanical energy. Mechanical energy at location 1 will be equal to potential energy plus again kinetic energy. Same formula we will use. And now potential energy is equal to mgh plus half mv square, which comes out to be, the mass is given to me almost, it is 800 times 9.81 times height value is 35 plus half times mass again is 800 times velocity is 4 square. So when I'm going to calculate this value, my final value, my calculated value of mechanical energy at location 1 will come out to be 2.81 times 10 raised to the power 5 joules. That will be the mechanical energy at location 1. And then I wanted to find what is the gravitational potential energy in the second instance. So at the second instance, we've said that this is an isolated system because it's a frictionless roller coaster, so it becomes an isolated system. So at this location, somewhere here, its kinetic energy is equal to, we're not given the kinetic energy, but we are given the speed. Speed here is equal to 20 meters per second. So correspond to 20 meters per second, I can find the kinetic energy, and from there I can apply the formula me at location 2, which is equal to potential energy plus kinetic energy. Kinetic energy is equal to half times mass value is, mass is again 800 times this 20 square plus this is the potential energy, and this mechanical energy will remain constant. I can file that value here, 2.81 times 10 raised to the power 5 joules. And by doing these calculations, I can easily find out the value. So this is 2.81 times 10 raised to the power 5, and this is potential energy plus this value will be equal to 1.6 times 10 raised to the power 5 joules. And then when I'm going to bring it on the other side of the equation, those values will subtract and the final value will come out to be 1.21 times 10 raised to the power 5 joules. I'm running out of the time, so I'm going to make it a little fast. So that's your answer for the second instance. So hopefully you were able to understand how to solve the questions on potential energy of an isolated system and the mechanical energy also. So see you in the next video. Bye now.